Simple linear regression is a useful tool, but often we imagine the values of the dependent variable depend systematically on more than just one independent variable. In this case, we use multiple regression to take account of all of these explanations of the dependent variable. Here, note that the equation looks fundamentally similar to the case we talked about in the last video, but in this case, there are several x variables, each one with its own coefficient. The interpretation is also a bit more nuanced here. The coefficient b1 is the effect of x1 on y controlling for or holding constant all the other x variables in the model. b0 is the expected value of the dependent variable when all of the x variables equal 0. Here, rather than just trying to figure out the effect of each variable, we are trying to figure out the independent effect of each variable. That is, what can each variable tell us about the dependent variable that none of the other variables in the model can? The relationships in multiple regression models we call partial relationships because they control for the effects of other variables. This is in contrast to what we talked about in the last video. We didn't give the relationships we looked at a specific name, but in the last video, those relationships are called marginal relationships. Marginal relationships are those that don't control or hold constant any other variables. If we want to try to make causal statements, we have to account for all other possible explanations of the dependent variable other than the one we're testing. Using control variables, that is, putting other variables in the regression model that capture other explanations of the dependent variable, is how we accomplish this in regression models. We might think that social unrest is going to be higher when places are corrupt, but it might also be the case that social unrest is higher in places with free press, because citizens might be more aware of incidents over which they ought to be aggrieved. Another reason that free press might explain social unrest is that it might be a proxy for a broader set of freedoms like assembly, association, speech more generally, and others. Here I estimate the partial relationship of demonstration activity on corruption and free press. You'll note that the effect of corruption is larger here, 0.39, versus 0.32 from the previous video. When we control for other variables, all coefficients can and probably will change. Here's the equation that we estimated. The intercept tells us that we expect demonstration activity to equal 1.06 when corruption is 0 and the country does not have a free press. For every 1 unit increase in corruption, we expect demonstration activity to increase by 0.39, holding free press constant. We expect countries with free presses to have demonstration activity 0.51 higher than those countries that do not have free presses, holding corruption constant. Holding constant means we are holding all other variables fixed at a particular value. In models like this one that are additive and linear in all of the variables, it doesn't matter which particular value we choose. It just has to be something. Let's take a closer look. Consider the equation that we've been looking at. Let's try to figure out the effect of corruption by calculating two predictions, changing corruption's values from 0 to 1, holding free press constant at 0. This gives us two predictions, 1.06 when corruption equals 0, and 1.45 when corruption equals 1. Notice that the difference here is 0.39, which is just the coefficient on the corruption variable. Now let's do the same thing, but allow press freedom to change from 1 to 0 as well. That is, both variables are changing as we move across the two predictions. This gives us predictions of 1.57 for corruption equals 0 and free press equals 1, and 1.45 for corruption equals 1 and free press equals 0. Taking the difference, we get minus 0.12, which is quite different from what we found before. When we don't hold free press constant, we get the wrong sense of corruption's effect. The reason is because this is not the independent effect of corruption, it's the effect of both corruption and free press changing simultaneously. Remember that we're trying to isolate the independent effect of each variable. The importance of this point isn't so much about the mechanics of this in an estimated model like we just showed, but it's really that we can only hold constant variables that are in the model. When we generate predictions for particular observations and think about what would happen if we change the values of a particular variable, that exercise only works well if we have accounted for all of the systematic factors affecting the dependent variable. This is a pretty strong statement and will often not be in this situation, but we need to be aware that failing to account for all of the systematic factors affecting y has important consequences on our ability to isolate the effects of variables. I want to talk about the assumptions of the OLS regression model. There are a few of them that we have to keep in mind. The first is that none of the x variables can be perfectly related to the other x variables. If this isn't true, then we can't find a unique solution to the regression coefficients. Ultimately, we want our regression results to be unbiased. This means that the center of the sampling distribution is the true population value. We took for granted that this was the case earlier, but there are estimation techniques where this is not the case. If we want our OLS estimates to be unbiased, then two other things have to be true in addition to the previous assumption. We need to have estimated the right relationship between the x's and y. We'll talk more about what this means when we meet in September, but briefly it means that if there are nonlinear or non-additive relationships, that we have appropriately captured them. The residuals also need to be unrelated to the x variables. This essentially means that there are no systematic variables affecting y that are also related to the x's that we have not included in the regression model. If both of these are true, then the results are unbiased. We also want our results to be efficient. Here, efficiency means that our results have as small sampling variability as possible. This allows us to make stronger inferences. For this to be the case, we need to add another assumption. That assumption is homoscedasticity, which means constant residual variance. What we mean here is that no matter which value of the x's we would pick, the variance of the residuals for that set of x's would be the same. There are some tests for this that we'll talk about when we get together in September. If our models are homoscedastic, then the results are maximally efficient among all unbiased estimators. Finally, to make appropriate inferences from our model, we need one more thing to be true. The residuals must have a normal distribution. If this isn't true, we might have unbiased and efficient estimates, but we still make inferences with the wrong type 1 error rate. I also want to talk briefly about inference in regression models. The great thing about our regression models is that we can use everything we've learned about inference before in this case. We can test hypotheses about the coefficients using t-statistics, where the t-statistic is just the coefficient minus the null hypothesized value divided by its standard error. Generally, you see the t-statistic as stated here, where it's just the coefficient divided by the standard error, because the null hypothesized value is usually just 0, and b minus 0 just equals b. The standard error is the square root of the residual variance divided by the sum of the squared deviations of x from its mean. And the residual variance is just the sum of squared residuals divided by the number of observations minus the number of independent variables in the model minus 1 for the intercept. Again, we don't really need to belabor the math here, but it's nice to know that we can use the t-distribution here just like we did in other cases.